Hello everyone and welcome to my YouTube channel. In today's video, we will create an artificial neural network from scratch without using any machine learning packages. So no TensorFlow, no Keras, no scikit-learn, etc. Our focus will be on predicting the prices of homes in Boston. Throughout this tutorial, we will break down the concepts of forward pass, backward pass or backpropagation, and gradient descent. If you are watching this video, I assume that you already have some knowledge of deep learning, hence some knowledge of calculus and algebra in order to understand all the technical details we will be looking into this video. That being said, today we will be working with the Boston housing dataset, which is a pretty famous dataset. You have it on quite a few data science websites. You have it on Kaggle, Fairlearn, and Path to Data Science. But you can also find it on universities' websites, such as the website of the University of Toronto, which is the website we are looking at here. That being said, let's look at the Boston housing dataset itself. The Boston housing dataset is made of 506 samples and 14 attributes. You have the definition of each of the attributes right here. Today, our target will be the median value of owner-occupied homes. Now that we have the dataset ready, let's try and look into the architecture of the neural network we will be creating today. To predict the prices of homes in the Boston area, let's create a two-layered artificial neural network. Let's make the first layer be of two neurons, W1 and W2, where each neuron has the linear rectifier activation function. And for the output layer, let's make it be of only one neuron without any activation function because we are dealing with a numerical target here. The linear rectifier activation function is a piecewise linear function which nullifies every negative inputs and keeps the positive inputs as is. Please note that for simplicity reason, I intentionally omit all the biases in this video. Moving on to the components of our network, the input matrix will have a shape of 404 by 13 because we will be working with 404 samples in this video and we have only 13 features. So we saw that the Boston housing dataset had 14 attributes, one of which is the target. So we are left with 13 features. Matrix W here represents the weight matrix of the hidden layer. So the first column of the matrix will hold all the weights of neuron W1 and the second column that of neuron W2. Now, because the input matrix has 13 features, each neuron in the hidden layer must have 13 elements. Looking at the vector V here, because we have two neurons in the hidden layer, the output layer must have two weights. Y is just the target vector, and because we have 404 training samples, the shape is 404 by 1. Looking at the cost function, we will be going with a simplified version of the mean squared error. Now, this is simplified because instead of having 404 in the denominator here, we only have 2. Now, that was a strategic choice because it simplifies the calculations down the road. Now that we have all the details down for our network, let's look at how the data traverse the network. There are two ways in which the data traverse the network. The data traverse the network from the input layer to the output layer and from the output layer to the input layer. So in the first way, which is from the input to the output, That process is called the forward pass. The second process from the output to the input layer is called the backward pass. Now let's look into the details of how the forward pass work in our case. There will be a dot product between the input matrix and the way matrix of the hidden layer. The output of that will be passed to the ReLU function, which will give us the output of the hidden layer. Now, the output of the hidden layer will be passed up to the output layer, where there will be a dot product between that output and the way matrix or the way vector of the output layer. The result will be our predictions, and we will input it to our cost function for evaluation. Before we move on to the details of backpropagation, let's code the forward pass first. For convenience, let's use the Keras library to load the data. That is the only use we will make of Keras in this video. So let's go ahead and do it. From keras.datasets import Boston housing. Now, Keras provides us the data already splitted for training and testing purposes. The only thing that we need to do is to provide it the variables. So let's go ahead and do it. So we have the X matrix, the Y vector, but also the test data and test target. The way to load the data is Boston housing dot load data. And that's it. Moving on to data preparation. How we will prepare the data is we are going to normalize our data. And the way to do so is we are going to divide the mean input matrix by its standard deviation. Here is what it looks like. So we will compute the mean over the columns, axis 0, and we are going to subtract those means from the values. So we are going to go x minus mean. Next, we are going to compute the standard deviation. So x, the standard deviation over the columns, and then we are going to divide the now demeaned input matrix by the standard deviation. And that is it. Next, let's try and create our way matrices. To do so, we are going to use the rand_n function. To get that function, we are going to go into the NumPy library, go into the random package, and import the rand_n function. So W here is the way matrix of the hidden layer. V is the way vector of the output layer. So for the W matrix of shape 13 by 2, rand_n will generate a matrix of random values of that size. For the V vector, we are going to go rand_n 2 by 1 because that is the size of the V vector. Moving on, we saw that the forward pass is actually straightforward. There is a dot product between the input matrix and the way matrix of the hidden layer. The output of it goes to a ReLU function to generate the output of the hidden layer. Now, that output is sent up to the output layer where there is a dot product between the output of the hidden layer and the weights of the output layer. And the result of it is our predictions. We are pretty much in a good shape at this point. The only thing that we are missing here is the ReLU function. Let's actually go ahead and code it. So we saw that the ReLU function is a function that essentially nullifies negative values. So for a given matrix, we will go through each of its elements, and if that element is negative, we will replace that value by 0. So let's go ahead and do it. So for I in range, matrix shape 0 to go over the lines, and to go over the columns for J in range, matrix dot shape 1. Here we are going through each line and each column, and if we find a negative value, so if we find a negative value, what we are going to do is we are going to replace it by 0, and that is the ReLU function. Now that we have the ReLU function, you are almost done with the forward pass. The only thing left to do is to find a way to quantitatively assess how good our predictions are compared to the target. And that is where the cost function comes into play. We decided to go with a simplified version of the mean squared error, where instead of dividing by the number of elements, we will divide by 2. But before we move any further, we're actually going to need the NumPy package here. So let's import it. So import NumPy as np. We move back down. So n, we will square the difference between the predictions and the target. We will sum it, and we will divide it by the number of elements. But here we are going with 2 because it's a simplified version of it. Let's actually reshape y here just to make sure its shape matches that of y pred. So reshape y and give it the size, and voila, we have just coded the forward pass of an artificial neural network. We are able to make predictions, and we have a way to see how good or bad our algorithm actually is. Let's go ahead and see how we are looking at this moment. So let's look at our predictions. We can see that the predictions are not so good. We have some negative values, and the values are in general quite small. Looking at the cost function, we can see that the cost function is huge. So we need a way to make our forward pass better, and that is where the backpropagation comes into play. So let's go back to our calculations to make it happen.